Today we will discuss about the topics UV spectroscopy. Now, first of all, we should know about the usefulness of the UV visual spectroscopy. First of all, we should know why we should use the UV spectroscopy. Firstly, to detect the number of conjugated double bonds and aromatic conjugation within the different molecules. Next, differentiates between the conjugated and non-conjugated system, and by the use of UV visible spectroscopy we can distinguish the alpha beta unsaturated carbonyl compounds from beta gamma analogues, and it also helpful to individualize between the homoannular and heteroannular conjugated dienes. This technique is also known as electronic spectroscopy because it involves the promotion of electrons from low energy ground state orbital to higher energy molecular orbital. Fixed quantity of energy is required for electronic transition, hence electromagnetic radiation with particular value of frequency will able to cause excitation, above or below of which will not be absorbed by the molecules. And substances absorbing in the visible range will appear colored to the human eye. The UV radiation region extends from 10 nanometer to 400 nanometer, and the visible radiation region extends from 400 nanometer to 800 nanometer. Near UV region belongs to 200 nanometer to 400 nanometer, and far UV region belong to below 200 nanometer. And far UV spectroscopy is studied under the vacuum condition. The far ultraviolet region, that is below 200 nanometer, is not much studied due to absorption by oxygen and nitrogen. Moreover, studies in this region require vacuum instruments. The common solvent used for preparing sample to be analyzed is either 95% ethyl alcohol or hexane. The container of the sample solution must be quartz shell, as glass absorbs UV light strongly. The most suitable source of light in the UV region is hydrogen discharge lamp, and that for visible range should be tungsten filament lamp. Now the question is, what is an ultraviolet spectrum? Ultraviolet spectrum is nothing but a plot of wavelength light absorbed versus intensity of the absorption. The wavelength at which maximum amount of energy required for a particular transition is absorbed appears in the spectrum as peak, and this is called the absorption maximum. Now from this picture we can see the absorption maximum. This is the lambda max value. For this compound, this is the lambda max value. Now we should be aware about the absorption law. There are two absorption laws. Lambert's law and Beer's law. Lambert's law. When a monochromatic radiation is passed through a solution, the decrease in the intensity of radiation with thickness of the solution is directly proportional to the intensity of the incident light. This is the source of light. Suppose the initial intensity is I0 and it passes through the sample, and finally the intensity is IT. Let I be the intensity of the incident radiation and x be the thickness of the solution, then minus di by dx is directly proportional to the I, or minus di by dx is equal to ki. Now we are coming to the Beer's law. When a monochromatic radiation is passed through a solution, the decrease in intensity of the radiation with the thickness of the solution is directly proportional to the intensity of the incident light as well as the concentration of the solution. Let I be the intensity of the incident radiation and x be the thickness of the solution and c be the concentration of the solution, then minus di by dx is proportional to c into I. That is minus di by dx is equal to k c into I. After combining these 1 and 2 equations and integrating the equation between limit I is equal to I0 and x is equal to 0 and I is equal to I and x is equal to L, we get ln I by I0 is equal to minus k c into L, or 2.303 log I by I0 is equal to minus kcl, or ln I0 by I is equal to epsilon c into L, where epsilon is equal to k by 2.303. This epsilon is called the molar extinction coefficient, or of the absorbing solution. Uh, it is directly related to the intensity of the light absorbed by the molecule. Hence, from the value of epsilon, intensity of the electronic transition can be determined. The term log I0 by I is known as absorbance of the sample, and it is denoted by the A. Formerly, absorbance was called optical density. Now, how to record the electronic spectrum? We know that the absorption of radiation by the molecule results in a transition from low energy ground state to higher energy excited state. The instrument that measures the change in intensity of the light is known as spectrometer. Now, here the picture has shown the function of the spectrophotometer. It has three important parts, namely source, detector, and records. Source, detector, and records. A source provides the electromagnetic radiation a particular frequency that pass through a given organic sample, mostly in the dissolved form. Detector. It measures the change in intensity of the radiation as it absorbed by the sample. And recorder. The change in the intensity of the radiation uh, as detected by a detector is recorded on the paper as signals, which are also referred to as peaks or bands depending upon the type of the spectroscopy. The change in the intensity of the radiation may be recorded as radiation absorbed for absorption spectroscopy or radiation transmitted for emission spectroscopy. Here, it is the process of instrumentation. Spectrophotometer, which is a device that allows light of a given frequency to pass through the sample and detects the amount of transmitted light. The most spectrometers are double beam instruments. The primary source of light is divided into two beams. Two beams of equal intensity. Before dividing into two beams, the incident radiation is dispersed with the help of rotating prism. The various wavelengths of a light source are separated with a prism and then selected by slits that the rotation of the prism causes a series of continuous increasing of wavelengths to passes through the slits for recording process. One of the beams selected one of the beams of selected monochromatic light is passed through the sample solutions, and the other beams of equal intensity is passed through the reference solvent. After the beams pass through the sample cell as well as the reference cell, the intensities of the respective transmitted beams are then compared over the whole wavelength range of the instrument. The spectrometer electronically subtracted the absorption of the solvent in the referred beam from the absorption of the solution. Hence, effects due to the absorption of light by the solvent are minimized. In this way, the absorbance or the transmittance characteristics of the compound alone can be measured. The signal for the intensity of the absorbance here versus corresponding wavelength is automatically recorded on the graph. The spectrum is usually plotted as absorbance against lambda. Types of source, sample, holder, and detector for the UV visible region has given there. For the ultraviolet region, the source is deuterium lamp and sample holder should be quartz or fused silica and detector should be phototube, PM tube or diode array. The visible region, the source should be tungsten lamp and the sample holder is glass or quartz and detector should be phototube, PM tube or diode array. Theory of electronic spectroscopy. Promotion of electron takes place from occupied bonding or non-bonding molecular orbital of the lower energy to unoccupied antibonding higher energy, from ground state to excited state. When molecule absorbs energy, transition of electrons from HOMO to LUMO takes place. Wavelength of light absorbed depends on the difference between the energy levels. We know lambda is equal to hc by delta E. Hence, for greater delta E, the shorter lambda, that is wavelength, of the light absorbed is required and vice versa. Now, here the picture of molecular orbitals involved in the electronic transition. This is the sigma bonding and this is the sigma anti-bonding. And similarly, for the pi bond, this is pi bonding and this is pi anti-bonding. And electronic transition occurs in this way. Here, from the picture, we can see that one electron jump from this non-bonding to pi star due to irradiation. Now, electronic excitation energies. When a molecule is excited due to absorption of energy, its electrons are promoted from a bonding to an anti-bonding orbital. Here, a list of transitions has given where molecular orbitals involved for electronic transition. Types of electronic transitions we have already seen in our previous picture. From molecular orbital diagram, it can be shown the different possibilities of electronic transition with different energies. There are different possibilities of electronic transitions from sigma to sigma star for alkanes, sigma to pi star for carbonyls, pi to pi star for unsaturated compound, n to sigma star for oxygen, nitrogen, sulfur, halogens containing compound, and n to pi star for carbonyl compounds. Here is a list of electronic transition, a type of electronic transition, and the molecular responses. Here we are seeing that sigma to sigma star transition occurs for alkanes, pi to pi star for alkenes, carbonyls compound, alkynes, azo compounds, etc. For n to sigma star transition, oxygen, nitrogen, sulfur, and halogen compounds, and n to pi star transition for carbonyl compounds. And the energy increasing from n to pi star to sigma star. Sigma to sigma star has the highest energy, where n to pi stars having the lower energy. Now we are discussing details about these electronic transitions. First of all, we will discuss about the sigma to sigma star transitions. The energy required for sigma to sigma star transition is large because sigma bonds are very strong. The organic molecules in which all the valence shell electrons are involved in the sigma bond formation do not show absorption in the UV region. For example, saturated hydrocarbon. The region below 200 nanometer is called vacuum ultraviolet region. This type of absorption corresponds to breaking of carbon-carbon, carbon-oxygen, carbon-hydrogen and carbon-halogen bonds. Now we are coming to the pi to pi star transition. And pi to pi star transition response for the compound olefinic compound having the pi orbital. This type of transition occurs in the unsaturated centers of molecules, that is the compounds containing double or triple bonds, and also in aromatics. The excitation of pi electron requires similar energy, smaller energy. Smaller energy is required for the electronic transition. Hence, this type of transition occurs at longer wavelength. Band due to pi star transition is also known as K band. Such band is very intense with epsilon max is of the order 10 to the power 4. With the introduction of methyl group, the olefinic linkage produce an increase in lambda x value. Such type of shifting of lambda max value to the longer wavelength is also known as the bathychromic shift, which we will discuss in our next day. Now we will discuss about electronic transition into sigma star. The saturated compounds containing atoms with unshared electron pairs, that is non-bonding electrons, responsible for N to sigma star transition. Compounds containing nitrogen, oxygen, sulfur, halogen can absorb via this type of transition. Absorption are typically in the range lambda range 150 to 250 nanometer region and are not very intense. Absorption maxima tend to shift to shorter lambda in polar solvents, that is in water or ethyl alcohol, etc. Now we will see some examples of absorption due to N to sigma star transition. For this compound, we will get two electronic transition N to sigma star at 290 nanometer and pi to pi star at 180 nanometer. Here in the picture, we can see the transition of electron occurs. Lambda max increases due to extended conjugation. Okay, from this to this, the lambda max is being increased. The important fact for UV visual spectroscopy that the molecules absorb the radiation. Two types of electrons are responsible. First of all, shear electrons that participate directly in bond formation, that is sigma and pi bonding electrons, and unshared outer electrons, non-bonding or N electrons. The shared electrons in single bonds, carbon-carbon, carbon-hydrogen, or carbon, that is sigma bond, are so firmly held, therefore not easily excited to higher E level, energy level. Absorption of sigma to sigma star occurs only in vacuum UV region. Lambda is less than 180 nanometer. The electrons in double and triple bonds are most loosely held, therefore more easily excited by radiation. Absorptions pi to pi star for species with unsaturated bonds occur in UV visible region lambda is where lambda is greater than 180 nanometer. In next day, we'll discuss details about the rest of these special topics UV spectroscopy. In our second lecture, we'll discuss details. Thank you very much for your patience sharing.